So we're going to be looking at the question of why do aircraft bank when they turn? Because when you fly, and birds as well, typically when your aircraft or birds are flying, they've got wings. And while we look at the top, they're kind of making this left turn over here. But they normally don't fly sort of flat. From the rear, instead of flying flat, which is what we might think from the top, they've actually banked in towards the circle. They actually slant towards the circle. And we call this here the banking angle. So there are actually a few particular terms called, I guess, pitch, roll, and yaw. So I guess this really here is the bank is really the idea of the roll. You're rolling to the left, okay? For those of you that are familiar with those terms. And this banking angle then means this plane can turn. But our question here is why does it do that? And it comes down to your force analysis as usual. So recognizing we're looking at this at the rear, so from behind, this is your engine spouting out some gas. Let's look at the forces acting on the plane. The most obvious would, of course, be your weight force going down. Now, there is the thrust force going forward. There's the thrust force going forward. There's the drag force going back. We're going to assume your plane is just going at constant velocity. So for now, for our purposes, they're equal. But we understand from our circular motion topic that basically we consider turns to be in a circle. So we know there's a net force to the left for the plane to go left. So there is some sort of net force that we require. And then you need to think about, well, where is this net force coming from? Because the drag is going forward. Right now, the plane's pointing forward. Most planes don't have engines that can thrust around. Rockets might, but most airplanes just go forward back. And so you really need to think about how that happens. So we've got the wave force pulling downward. There's no normal force because the plane's in the air. But what you do have, if you might recall, from a typical plane, for your typical plane, we've said before that your typical plane has 4 forces acting on it in general. There's the thrust going forward. There's the drag pulling back. There's the weight force pulling down. And there's what's called a lift force pulling it up. But the lift force comes from the wings, which is not strictly up necessarily. Just like the normal force, it depends on the orientation of the wings. The normal force depends on the orientation of the ground surface. The lift force also depends on the wings. In this current situation, my wings are slanted, which means when my wings generate lift, my lift will be in this direction. And that is actually going to be helpful because if my lift is in that direction, I'm going to get a lift to the left in the horizontal direction and a lift in the vertical direction. And just like in similar questions where you've done, for example, your inclines, when in year 11, where the normal force has a horizontal and a vertical direction, you now have a component to the left and a component up. And so just like your inclines, your component up will match your weight force if your plane is flying level. But now you've got this left one, which is now going to help. So this net force actually going to the left comes from your lift, horizontal component. So that basically is what contributes to your circle. And you can see parallels with this when you look at banked tracks questions, when you've got cars on banked tracks. And you can see similar parallels with your year 11 work when you've got your cars on inclines. So let's now try and apply this. Let's imagine that you now have a plane. This plane is traveling at a velocity of, let's say, 500 kilometers per hour. Not the fastest plane. And let's say they want to make a left turn. and they want to make a left turn with a reasonably large radius of 2 kilometers. Not too large, not too small. Now, we understand that the forces in question, as we discussed, so we'll draw it as a box now. You've got the weight force going down, and you've got some lift force. And that lift force angle is dictated by the bank angle. So your bank angle is between the horizontal and that. So this is your bank angle. Now, the bank angle theta is what we're trying to find, is going to also equal this angle here, which means, of course, if this is theta, this is 90 minus theta, so this is theta up here, which then means for my lift L, this is going to be L sine theta, and this is going to be L cos theta. So what that then means is your centripetal force must equal your lift horizontal component, which is L sine theta, where theta is the bank angle. But we also know that we don't want the plane to fall out of the sky, right? This is the horizontal situation. But certainly we're assuming that plane flies in the air, it stays constant. So that means vertically we've got the L cos theta, which is upward, minus weight must equal 0. So that lets us work out lift. Just like before when we can work out normal, we can now work out lift. So the lift in terms of weight, L cos theta equals weight, or L must equal weight over cos theta, which is equal to mg over cos theta. And as I said before, you can probably see some parallels with your normal force. Now, centripetal force is mv squared over r, must equal L times sine theta, which is equal to mg over cos theta times sine theta, which is mg tan theta. Now you can cancel out the m. So you can see that the banking angle you need is really just you can just type in your radius, your g, your v, and to work that out. So in general, tan theta must equal v squared over rg. We just now need to actually get numbers now. So r is 2 kilometers, which is 2,000 meters. Remember SI units always. V is 500 kilometers per hour, which we could change into meters per second, which is basically 1,250 over 9 meters per second. So that then means, subbing numbers in now, tan theta must equal 1250 over 9 all squared divided by 2,000 times 9.8. Give you an answer of 0.98. So looks like I've made it like a fighter jet or something, because that now needs a bank angle that is very high, 44.54 degrees. So usually your bank angles are much lower than that. So I probably picked a radius that was too small in real life context for most planes. But that is basically how you do it. That's how you link the bank angle based on the velocity of the plane and the radius that they want to make their turn. So 2 kilometers is still really small, tight circle for something traveling at 500 kilometers per hour. And that's basically why they bank, to be able to turn.